everyone. My name is Zhi Li. I'm a postdoctoral researcher at Hydrometeorology and Remote Sensing Laboratory at the University of Oklahoma. Today, it's my real honor to present you my research work entitled "The Contaminous United States is projected to become more prone to flash floods in a high-end emission scenario." At first, I want to draw attention to some of the recent or historic floods happened this summer. Those are statistically 1 in 1,000 year floods across the country from the west to the east, starting from the St. Louis flooding on July 26th, and then the eastern Kentucky flooding on July 28th, southeast Illinois flooding on August 1st, Death Valley flooding on August 5th, then the more recent the Dallas flooding on August 22nd. Those are devastating flash flood events in terms of its direct and indirect damages to local communities. And the urban flooding itself caused many troubles in the communities to get resources and recover from those devastating events. Worldwide, we have also many flood events happening. For instance, the Pakistan flooding happened last month is a typical one that killed over 1,000 people and displaced over 1 million people. So in a warmer climate, we expect to see more and more such extreme events because of more vibrant storm or atmosphere as itself can hold more water vapor. And I want to highlight several challenges in flash flood projection, as you may have heard of the flood projection using climate models. Flash flood is really a subset of flood that is onset within several few hours of onset of extreme rainfall. In that sense, we desire high resolution climate projection data. Most of the climate data models produce the very coarse resolution at 100 kilometer scale, for instance. But the flash flood scale is really looking at kilometer scale, 1 kilometer scale, or if sub 100 meter scale. For the temporal resolution, we're looking at hourly or sub-hourly data set, and those of which those current climate projection, modern climate data set cannot resolve such high resolution atmosphere. Also, I want to highlight acknowledge the uncertainties in climate internal variabilities that is due to the uncertainties in the initial field and uncertainties in the model structures, parameterization, physical schemes, etc. Those of term combined together, we cannot really accurately project the future climate. Those we have to use the very wide uncertainty spread to characterize the future changes in the climate states, such as the air temperature depicted below. And there being lack of continuous rainfall simulation in modern climate models, even though those models have coupled with land surface, they do not really resolve the stream flow prediction over the globe. So those three challenges combined together, we have few studies quantified the changes in flash floods. In light of that, we proposed a methodology to quantify the future flash floods by using a high-resolution climate projection that is a dynamically downscaling scheme. Basically, it has high-resolution climate simulation over the continental United States at hourly and 4-kilometer resolution. It's a convection permitting model that so that it can resolve the convective scale precipitation by itself instead of parameterizing it in the models. For the historical or contemporary climate, we had this retrospective simulation forced by 6-hourly error interim reanalysis data from 2000 to 2013. For the future climate, which is a pseudo global warming scheme that is basically perturbing the horizontal winds, geopotential, temperature, humidity, surface temperature, soil moisture, etc., using an ensembling of an array of simplified models from a high emission scenario that is RCP 8.5. We also applied the spectral nudging to reproduce those synaptic weather events to well represent those historical atmospheric events. So those climate model only simulates atmospheric states. We also need the hydraulic simulation to handle the land surface stream flow prediction. So here we use the ensemble framework for flash flood forecast, the EF5, that is operated by the National Severe Storm Laboratory here at NOAA. It has a couple of models that can be used as an ensemble framework to predict the stream flow. We simulated this climate simulation for 2001 to 2013. For the model, we choose the SNOW 17 plus the CRISP, short for couple routing and access storage. For the model resolution, it resolves grayscale at 1 kilometer and outputs the stream flow data at hourly time step. For the model inputs, it ingests data, precipitation data, temperature data from the climate simulation and outputs the stream flow and soil moisture. To quantify the flashness, we propose the term that is basically, if you look at the hydrograph, that is the flood peaking time, TP here, and the flood magnitude, QP here. That is basically, if you see an increase in flashness, that is due to either an increase in high flow magnitude or a shortened flood peaking time. If you look at the future hydrograph, you can notice that we have higher flood magnitude as well as a shorter flood peaking time that is really conducive for flashy floods in the future. And to quantify the spatial scales of extreme rainfall and floods, we promoted this term rainfall spatial scale and flood spatial scale, both of which are derived using this method. That is, we first calculate the 2-year rainfall or flood threshold. Once the flood or rainfall events exceed that threshold, we calculate the distance between the central point to the farthest 8 vertices. For flood spatial scale, there are several additional steps required to account for the spatial discontinuity in the flood occurrence. Here, after we calculated the flood threshold, we created the binary co-occurrence matrix with number of rows indicating the number of days and columns indicating number of pixels. Then at each time frame, we cluster those flood points with an unsupervised flood machine learning algorithm called the dbScan. The advantage of that is we can ignore some outliers that basically they're not collected spatially. And finally, we calculate the central point and the max distance to the edge point as a proxy to the flood spatial scale. Then because we also want to look into the dynamics of the post-rainfall and the floods, so we quantify the seasonality using 2 terms illustrated here. The first term seasonality is very apparent. That's basically the most occurring flood months across the year. And we also have the strength of seasonality by looking at the distribution of the flood occurring months. If it's uniform distributed or having very weak seasonality, that means the flood can occur any month of the year. If it's more concentrated seasonality, that means we have very strong seasonality. Basically, it tells you that flood is more likely to happen at a particular month, let's say in May or April. This map shows the extreme rainfall changes. On the top, it's the extreme event rainfall for the mean and extremes. On the bottom, and the associated percent change. So we see a median of 24% of increase in extreme rainfall in the future. That is several regions you can see that are highlighted are the southern plains, Midwest, Deep South, etc. are likely to experience more extreme events, extreme rainfall particular in the future. For the spatial scale of rainfall, we plotted here in terms of different climate regions, but they're ranked from west to the east. As you can see, from the west to the east, there's been increase in rainfall spatial scale that is almost double the current rainfall scale, spatial scale. And we also investigated several events, and we can see those, for instance, those individual extreme rainfall events are likely to combine and form into a one large single thunderstorm in the future. Basically, that's almost double the current rainfall spatial scale in the future. We also see changes in flow signatures. For instance, we have seen this decrease in rainfall duration and flood duration in the future, but an increase in the flow volume and rainfall volume, rainfall intensity and flow intensity, flow rates, particular in the future, and a decrease in the lag time. That's basically when the lag time between the rainfall peaking and the flood peaking time. As a result, you see a substantial increase in flashness in the future that is highlighted here. For rainfall and the flood seasonality, also if you look from the west to the east, you can see the month composition is more complex, meaning that the seasonality is weaker as you move from the west to the east. That is due to these more complex inland weather systems driving the atmosphere, as well as the flooding will follow the similar pattern. We do not see major differences in rainfall dates if you subtract the future rainfall seasonality by the current rainfall seasonality, but we do see a weaker seasonality strength in the future. This is a similar thing for floods. You can see there's decreased seasonality for future floods. And for flood dates, you can see over the Rockies, the flood is occurring earlier than current climate. That's due to the snow melt. But in the east, you can see the delayed peak flood dates. That is basically we speculated that due to this drier soils in the east. As a result, we see both extreme rainfall and floods in the future are becoming more random, that is less seasonal. And earlier snowmelt leads to earlier floods of the Rockies. Floods in the east are delayed due to their drier antecedent soil moisture. As a conclusion, we have seen that United States floods are becoming flasher, extreme rainfall and floods are becoming more frequent, widespread, yet less seasonal. That is a weakening seasonality. Flood generating mechanisms are changing, and we need to design our flood measures in an evolving manner to cope with those changes. That is all for my presentation. This slide summarizes all the references I used in this presentation, and I'll thank you for your attention. If you have any questions, feel free to contact me through this email.